when we look at a drawing, so a large part, in fact, this entire first unit, in my opinion, is just structure. How do we look at structure? How do we evaluate structure? What does that mean as far as energies? And we look a little bit at its application. We look at intermolecular forces, right? But if we go through and look at structure, we could draw a cyclohexane with 2 methyl groups on it. And we could reference them both being up. So I've got them color-coded as red and blue here. That red and blue overhead view, as it is commonly known, misses a lot of key information. Okay? The information it misses is the relative location of those methyl groups to each other, okay, in space. That's why we could then move to a chair. Right? The chair conformation is now taking a look at that structure from the side. Okay? So we've got the chair drawn above. This is where we'd put our feet, and this is where we would put our head in the chair. The 2 atoms below, okay, the overall chair in the 2-dimensional drawing here, are the atoms coming out at you. Okay, so those 2 carbons are coming out of the plane of the board at you. The only 2 atoms that are in the plane of the drawing are the head and the feet. Everything else is either in front of the drawing or behind the drawing, or the paper. Okay? How does that translate from our overhead view? Okay, well, with those markers on there, it helps. That would be feet, and that would be head on our overhead view. So what we have done is taken that structure, kind of pulled it up out of the page, flipped it forwards, and then turned it. Right? And that's how we're now viewing that molecule. When we go through and change our viewpoint on it, we notice that the methyls, the red methyl and the blue methyl, are still both aimed upwards. The red one might be a little bit more difficult to see because it is in a slightly different orientation than the blue one. The blue one, hopefully everybody can see, is clearly pointed upwards, right? Yes. The red one, how do we see if that's pointed upwards? Okay, well, its position is different than the blue. Its position is what is known as equatorial, and the blue one is referred to as axial. The axials are typically easier to see because they point up and down. The equatorials become a little bit more challenging because they tend to point more flat. What makes this extra difficult is that when you draw it, your chair sucks. Okay? Which is fine. Okay? That's not a big deal. We just have to acknowledge where those weaknesses are and try and align and account for those things as best as possible. That's why we had earlier slides just depicting how to draw a chair. Okay? It becomes important because it helps you to see those spatial locations. If you don't know how to draw it, then those spatial locations get easily lost. Some people are like, it's easily lost already. Draw it, and it makes it that much worse. Okay, so what we're trying to do is become as zeroed in on a common way to represent these things as possible. Okay, so we definitely get this equatorial versus axial situation. Okay, if you've drawn your equatorials nicely and perfectly, you will notice that that red, now red arrow is slightly aimed up. Okay. So if you've drawn your chair correctly all the way through, your equatorial positions will be aimed up or down. That doesn't mean your drawing shows it. So what would be a nice way to ensure that you get your equatorial labeled correctly as up or down? Every carbon of the ring has an axial, one axial, and one equatorial. Is the axial easy to see? Yes. The equatorial is difficult. So what should you do? Identify the axial. Whatever it is, the equatorial is the opposite. The axial here for our hydrogen is aimed clearly down, which means our equatorial must be up. They're both wedged, that matches the overhead view. Okay. Other thing to be careful of when we're doing these manipulations is to ensure that we haven't changed our numbering. What do I mean by that? Start at that 1, 2, 3, 4, 5, 6. When I go to the chair, 1, 2, 3, 4, 5, 6. What do I mean by change numbering? Isn't this still going to get me 6 carbons to count the numbering that way? Okay. It gets that. We can address that too, nomenclature-wise. Okay, it's not going to be an issue there, but there's a larger issue here. That issue is chapter 5. If I change the numbering, I'm now changing the location of where I'm drawing that second methyl. That can have a drastic effect on my overall structure. So much so that the structure I end up drawing is not identical to the structure I started with. So you need to make sure that you number in the same fashion. We numbered at the bottom. I numbered going which direction? Counterclockwise. If we look at the numbering currently on my drawing, that is clockwise. I've changed the direction. That makes a really big deal. Okay, so if we double back through with our drawing, fix the numbering 1, 2. That's as far as I need to go. The second position is where that methyl's located. There we go. We've now got a chair with those groups on there. Okay. We also addressed that we could now change our viewpoint yet again on the molecule to get a Newman projection. Those of you just in the lecture were probably not forced to look at the Newman projection and just saw the images and were like, what the hell does that mean? Okay. Those of you who were in the lab were forced to do it and try to interpret it. You probably still concluded with what the hell does that mean? Okay. That's okay. You just have to realize where those issues are. Okay? So, if we now go through to layer that information onto my chair, right? Conveniently, I picked an awful way to look at this. Oh well. This bottom carbon here would be feet. This top carbon would be head. From that bottom carbon, I know I have a CH3. That CH3 would be aimed directly at me, which is going to be insanely hard to draw on here. Okay, we're to represent correctly. So we can just draw a straight down CH3. Where's the blue? To my right, to my left. I'm going to have to go to the right. If you think about the eyes drawing in, if that's my feet, to the right is where I'm going to have that CH3, behind the plane of the board. Where was that CH3 located? Straight up. Where's straight up from that carbon? That hydrogen needs to be a CH3. What we've now drawn is a Newman projection on this structure. This Newman projection is not the greatest, right, because it doesn't allow us to see the relationships of both the equatorial and the axial. And I should have thought about that before I started labeling things. Okay, but it does at least get us our methyl. And we can now draw an interpretation here. That methyl has a particular Newman energy or Newman depiction with the rest of the ring. That methyl is incredibly close to that back head carbon. Right? And this is where people go, well, what's incredibly close? It's not connected to the same carbon. It's behind it. Right? So it's kind of like that. I've got one hand out front and one hand in back. Okay? That interaction brings them close to each other, which makes it gauche. Gauche, whatever you want to call it. I don't care. Okay, so we've got the gauche, the G interaction. Okay? That interaction is not a favorable interaction. Okay, so what does it try to do? What does that methyl try to do to get away from that CH2? It repels downwards. As it repels downwards, what happens? Okay, it will become equatorial and it will undergo, or it will force, a ring flip. That ring flip is going to change where everything is located. Okay? How much does it change it? Significantly. That head will now get forced down below. And then that methyl gets shuttled out to the side. Okay, for those people being like, dang, how did you draw that experience? You should get that experience by doing this.
Shouldn't the
Oops.
methyl group be on the
And even with experience, I screwed it up. Okay? Now when we look at that same interaction between the CH3 and the old head, where are they located? Okay, and I heard a fun word there. They're located axial. No! This is why it's extra confusing. We had the axial position, which resulted in a gauche interaction. We now have an anti-interaction, which means the methyl is now equatorial. Okay? Notice where that CH3 is. It's no longer directly on that up-down axis. It's rotated off to the side. Okay? If we'd picked a better Newman projection, we could have gotten both of those in the same one. Should we try and do that? Yeah? Okay. You're jerks. Admittedly, I asked the question. So we're going to move our eyeballs around. You ready for this? Here's your eyeballs. Not aiming that way. So, Newman projection of relevance is the one on the right. Okay? That dot in front would be our feet, okay, or what I have labeled as feet. So I'll call that orange and feet. The CH3 is aimed out there. Connect these up. Does everybody see it?
Yes.
And I believe what I've now drawn is the correct chair conformation, or the correct overhead view for this molecule. Notice there's our gauche interaction. Notice there's an anti-interaction. Do you notice anything else? What's that interaction?
Go.
Another gauche interaction. Okay. Turns out that gauche interaction, we're not going to be able to do anything about it.
Wait,
Okay.
so this won't flip? What do you mean by won't?
Won't be able to do anything about it because of where those groups are located. They're always going to be gauche to each other.
Oh, I see. I thought that
Let's
was
check.
flip.
Let's check. So let's go ahead and flip it. The good thing I left lots and lots of space to do that flip. So as I flip, yep. Do that? I think I got it. And what did I say? There wasn't anything we were going to do about it. It's still gauche. Right? What changed? Well, the red group is now gauche to the ring. The blue group is now anti to the ring. Notice the energies. Gauche, gauche, anti, gauche, gauche, anti. What does that mean? Is either one of those chairs more stable than the other? No, they have the same energy. Okay? Did we have to go all the way out to the chairs to find that information? Well, the reason we go to the chairs was to acknowledge that when we were this red one here, we had an anti-interaction, and that red meant equatorial. The blue one was gauche, which meant axial, back to our overhead position. So if I go through and I memorize that the gauche interaction comes from an axial position, and the anti-interaction comes from an equatorial, what can I do?
Not draw it anymore.
I cannot draw it anymore, and I could immediately go through and look at my chair and reference all of that. Can I delete all that? Because that looks like an awful mess, and that's bothering me a little bit. Yeah? So if we clear all of that away, of course I cleared everything away, I could look at this and say this was equatorial, this was axial. Equatorial was anti, which is good or bad? Good. Okay. Good's a little vague. Let's fix that up. Let's not do good. Let's do low energy. Stable's another good word to throw in there. Stable. What happens with the blue?
It's gauche.
Axial, which came from a gauche interaction, which was
Less stable.
high energy and less stable or not stable. Okay? So cool. The axial's bad, the equatorial's good. So what could I try and do?
Make there be a-
Find it.
I could do a ring flip. Okay? See what happens if we had aligned the other direction. When I go through that chair flip, what happened to each of my positions? And this is where things become challenging. This was our foot, right? The foot became what? Where's the head? Okay, that's my new head. When I do that flip, that CH3 becomes axial. Where's that blue CH3 located? Okay, in the crevice corner behind the plane. It's back there. Whoops. Yep, I drew that right. CH3. The CH3 is now equatorial. Fantastic. That's exactly what I wanted. So this chair must be more stable, right? What happened to the other one? It's axial. As we go through the chair flips, we will exchange between equatorial and axial. So from the chairs, I can see that they're going to be the same energy. It doesn't matter which one I draw. Okay? As long as I have that Newman backing to get me there. Kind of, sort of? Don't have the Newman backing, then are you screwed over? No, because what can you do? Memorize what? Equatorial is more stable than axial. That will answer your chairs. Yes, when it comes to Newman, you also have gauche and anti that you have to deal with. But that doesn't have to come in with the chairs. Doesn't have to. Ish? Enough? Okay. Model kits. Okay, the model kits will help you visualize and see this. After that, it comes with lots of practice in dealing with those manipulations. Okay? So there was all that. We summarized all that. So we're going to move through. Hayworth was the side view we talked about, which really gets us to Chapter 5. Okay? Chapter 5 is my least favorite chapter because when it comes to trying to establish the relationships between structures, I have to draw them. Right? I have to draw lots of structures. And so I'll usually get students or people more advanced just being like, no, those are enantiomers of each other. Can't you see that? If I could see it, I wouldn't be drawing it. Back the heck up. Okay? So it is a challenging subject or area to deal with because you're trying to deal with those spatial responses. And what I have personally found is that if I do not draw them, the odds of me making a mistake go up drastically. Okay? You get to decide where your threshold is. Okay? So let's start with what chiral versus achiral is. Okay? All structures have a potential for a handedness. Okay? A hand is chiral. Okay? And that sounds kind of bizarre, but all you have to do is talk to a left-handed person, and you will find out that hands are very chiral. Okay? Just give them a pair of scissors and see how many times they stab you with them. Okay? Scissors are chiral just like your hands. That's why they fit in your right hand. And if you switch to your left hand, they don't. Okay? There's a handedness associated with it. Okay? That handedness can be derived out into this definition. Chiral is non-superimposable on its mirror image. Okay? There are a variety of kind of cheats and shortcuts the textbook goes through and that I will go through as well for organic chemistry that will cover you for 90% of the questions. There's that 10% that go back to this hardcore definition of superimposability. The hands works great. Okay? The right hand is non-superimposable on the left. If I put a mirror in between, it reflects across perfectly. That's your mirror image. Okay? Before we get too excited about clapping and being like, they're totally superimposable, superimposability means the bottom of my right hand must overlap with the bottom of my left hand as well as all the fingers. That's not going to happen. Okay? That's because your hands are chiral. There are some objects that are achiral. Chairs. Okay? Your butt is achiral. Okay? So the chair that it interacts with will also be achiral. Okay? Those would be superimposable on their mirror image. Okay? How do we find out if they're superimposable? Well, with the chair or your hand, you try and just slide it across. Okay? One of the things that can be difficult with molecules is that you aren't used to dealing with those objects in 3 dimensions, and it becomes a lot more challenging to manipulate. Okay? How challenging? This concept was first discovered by Fisher, I want to say, when he was studying wine. Okay? So long time ago. And he noticed that certain crystals of tartaric acid in wine reflected light differently. And he could manually, by looking through a microscope, see how the light moved differently and separate the crystals away from each other. Okay? Imagine taking salt crystals and tweezing out each crystal into separate piles. That's effectively what he did. Okay? So that's kind of a neat observation. But really all it was a parlor trick. Okay? Because we didn't understand why it was important. Okay? So we continue on. About 1950s is when we get the most famous kind of occurrence of it, and the drug that we've got is thalidomide. Okay? There's this interesting new type of bond style here, that wavy bond in there. That wavy bond says, I'm not going to specify if that's wedged or dashed. Okay? You notice all the other atoms, or all the other bonds are normal, just solid lines. We don't see any wedges or dashes. We don't really care. That particular bond and that particular carbon, if we change that squiggly line to be a wedge versus a dash, those two molecules become non-superimposable. Okay? One bond aimed up or down, and all of a sudden your structures now don't superimpose on each other. Okay? The initial thought was, not a big deal. Okay? So they created this drug, fantastic at curing morning sickness. Okay? So pregnant ladies, awesome. You don't have to worry about morning sickness anymore. Fantastic. Okay? You just have to wait 9 months to find out that the other molecule that they didn't bother to separate out mutated your baby. Right? Because they're like, it doesn't do anything. We don't really care about it. They didn't do enough studies to see that single change made a really big deal with how the human body processed that drug. And it turns out that one of the byproducts of the other structure is a mutagen, a very severe mutagen. And if you've heard reference to seal babies, that's where it came from. Okay? So massive, massive issues with extremities? Is it extremities? Okay? Where arms didn't form properly, fingers didn't form properly. Kids were born with effectively flippers, okay? Because the bones just didn't form correctly. Okay? All due to a byproduct of that drug. Okay? So it caused massive issues, and since then, we've at least attempted to be a lot more cognizant of the concept of chirality and making sure that when we go through to make drugs, that if there are chiral atoms, we address that very, very carefully. Okay? So as a concept, it is difficult to manipulate and see. We will see it pop up again and again and again through all of our syntheses. So when we run a reaction, we have to watch out. Is this going to make a mess later on, or is it going to be nice and simple and straightforward? Okay? So, classification of molecules. This was our simple pass. Okay? This got us really to 4 categories: different, identical, stereoisomers, and structural isomers. Okay? The flow chart is giving you questions that you need to be asking along the way. There's 2 big ones that become challenging. Only one shows up first: superimposability. Okay? That aspect of trying to get them to superimpose. Okay? Let's see. Of course, we don't have any pens because that would make things too easy. Right? If I asked you to draw that pen, right, how would you draw it? Black cap down, rest of it up. Cool. Okay, how about that pen? Black cap up. Okay. So you put them next to each other, and this is what I'll get people saying. Those are not superimposable. Yes, they are. Okay? And one of the questions that will typically come out of this section is, I'm allowed to do that? Yeah. Yeah, and it gets worse because that one was relatively simple, right? You know, I just had to release my hand a little bit. Okay? We could have also drawn the structure like that. And where now all you see is a black cap. And in the drawing of that black cap, you also have to acknowledge the rest of the pen is there, and you would have to do that rotation to flip it down. Those 3-dimensional manipulations are all things that you are responsible for. You have to be able to do. Okay? Some of that comes from just being able to understand the 2-dimensional drawing. Most people are horrible at that, and you need some kind of secondary backing behind it. Okay? That's where the model kits come in. Okay? When I say most people are horrible at it, they're like, no, I'm not. I do pretty well. And I go, okay, let's actually test your ability to do it. They're like, see, I'm right. I did this one right. I'm like, okay, do another question. Oh, I did that one right too. Okay, do another question. Okay? When we get through 10 questions, you will have done 5 right. I'm great at it. You're 50%. You are literally guessing. Okay? So be careful when going through and looking at these relationships with kind of cheats or shortcuts, because oftentimes those cheats and shortcuts are really no more than a coin toss. Okay? It really does require very careful manipulation of the structures, okay, in 3 dimensions, and making sure, remember when we did that counting thing around the ring, that you maintain your counting systems as you manipulate structures. Okay? It is challenging to deal with, and it requires some very precise accuracy behind it. Okay, to that end, we've got our first example up at the top. We've got 2 structures drawn. Okay, do they have the same molecular formula? Yes. Are they superimposable? No, they are not superimposable, and yet we heard a very overwhelming audience participation here of saying, yes, they were. No, they're not. That is why this is a difficult concept to deal with. Okay? So for those of you saying, yes, they were, here's the carbon backbone, there's the carbon backbone over here, right? Well, that's not what I meant. Come on, scribbles. Okay? If I tried to superimpose those, would those superimpose? No, so that didn't work. So what's the first manipulation we do? We flip the structure. Now, of course, I colored over everything. Oh, well. So I'm going to take that structure, and I'm just going to kind of flip the whole molecule. So when we flip that whole molecule, it goes boom, 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 and it superimposes. And you're like, dude, Mike, you're an idiot. That chlorine was aimed at you, right? Flip the structure. It's now aimed away. That blue chlorine's back here. Are those chlorines superimposing with each other? No, those are not superimposable structures. Okay? That is a challenging concept to deal with. Okay? In general, it's easier to overlap the carbon backbone first and then identify where all of your groups are located. This is a relatively simple one. Okay? So it wasn't as big of a deal. Okay? But I could have gone through and instead of superimposing the carbon backbone, said I wanted the chlorines to superimpose. So if I did that, I would have to take this structure. This is awful. So that rotation we did was kind of on the y-axis. This is going to be awful. Trust me. No, it's not too bad. I'm now going to rotate in the plane of the paper. I think. Look at that. Pulled it off. Yeah? The plane of the paper just
Is
like
that a
clock.
rotation?
You use the appropriate F letter sequence for that. Potentially. Now the chlorine's wedged, right? So could we overlap the chlorine?
No.
You mean I couldn't just overlap the chlorine there, right? Wouldn't it be overlapping? Yeah, it would. Would the carbon chain then overlap? No. Okay. That's a little bit harder to manipulate. Sometimes people see that carbon chain better, so it's up to you on which one you go through. That version I just walked through, I don't see easily. And if it was a serious question about the z-axis, I think so. The axis coming out at, yeah, so that would be the z. Okay. My inappropriate response to that, for those of you that aren't in the lab, has to do with questions that came in the lab procedure or the lab activity on flipping on certain axes. Smart work will ask you those. I will ask you those when I have control over you to be able to define where those axes are. And it's a very difficult question to ask on an exam because I don't have control over you. Does that make sense? Okay, so if you're freaking out that you might see those questions on the exam, you should not. I hope not. I made it a while ago. I haven't looked at it in a while. Okay? Kind of getting the idea of the difficulty behind this? Understand the manipulations we got to work through. Okay. So, stereocenters hinge on finding asymmetry in that molecule. Sometimes that asymmetry is easier to find than others. Okay? Sometimes it's not. So, with our cis trans, we get an asymmetry because they're non-superimposable. They're aimed different directions, right? And that can help if we color code sometimes. Whoops. We can see the R's are on the same side versus, opposite sides of that double bond. Everybody get that? Okay. If we look at the rings down below, remember rings have the same properties as pi bonds because rings are just an extended pi bond through multiple atoms, okay? Or pi bonds are really just a shrunk down ring, okay? So we still get the same kind of cis-trans issue. The atoms are still connected to the same locations, but they're spun slightly differently in space, okay? Where it becomes harder is when we shift out to atoms along these lines, okay? Why are these atoms a little bit more difficult to manipulate versus these ones? They can be rotated. In particular, these structures cannot rotate around the pi bond or the ring. They're locked in place. As soon as we move to these, all of a sudden we can do all sorts of weird rotations. Why can we do weird rotations now that we couldn't do before? Okay? It is our sigma characteristics or the lack of and our lack of rings. That sigma bond allows free rotation of individual bonds. Okay, so we not only get the molecular motion, but we also get internal atomic rotations that can make things more challenging. If we take a look at the top section, we reflect across the mirror. Okay, we've got our mirror image. Are those superimposable?
Yes.
Okay, if we take that leftmost structure and we rotate it, the green atom stayed in the same place, so there's one. Kind of bothers me that that's not green. We got our 2 over here. What happens with our 3? Those 3s align. They're labeled as 3s because we can't tell the difference between them. For those of you who know, well, 3's in front versus 3 in back. I can't tell that difference. Because remember, I can change my viewpoint around anywhere on that molecule. When I move to the one below, instead of it being a 3, you'll notice that it has become a 4th atom. So that if I do that same rotation about that bond, what happens?
Not super.
As I do that rotation, 3 that was in front is now going to be in back. The 4 that was in back now becomes in front. Now when I try to superimpose and slide that over on top, it doesn't superimpose. Kind of see it? Okay. That is our big red flag for a chiral atom. That is asymmetry in the molecule. Okay? Because I can't do an internal reflection, okay, or an internal mirror plane. So our cheat for most of OChem is to look for a chiral carbon, okay, or a chiral center. Okay? That tends to be a carbon that has 4 distinguishable things bonded. Okay? Notice I'm using a different word than fudge, different. Right? Because distinguishable just means that I can tell a difference between those 2 positions.
So it doesn't have to be 4 different elements. It could be 4 different carbons and it's still.
Yes. Just to be a bit of a jerk here, let's try this. Are those carbons distinguishable? Yes. Why? They're color-coded. Yes. Fantastic. Okay, except in the real world, we can't color-code them. Okay? So they don't get color-coded as those markers. I'm color-coding them as a way for us to think about and look at this. Okay, so realize all 4 of those are indistinguishable from each other. Yes? We okay with that? How do I make them distinguishable? What did I change? Say that again? What it's bonded to, right? Instead of being bonded to a hydrogen, it's bonded to a D. You can do better than that. Deuterium. Okay, heavy hydrogen. That red carbon is now different from all the other ones because it has 3 deuteriums connected to it.
Is that an element on the periodic table?
What is deuterium? It is a hydrogen with an extra neutron, so it has 2 things in the nucleus. It makes it heavy hydrogen. Okay, so deuterium is hydrogen. Okay, that is enough that we could now distinguish those. Okay, or that red carbon from the others. Okay, do I have a chiral atom yet? No, why not?
Still have C3.
The other CH3s I can't distinguish from each other.
Still.
I still know because I can't distinguish yet, right? Okay, just checking. Still no, okay. Yes, I know.
Please stop.
This is Franken molecule.
2, 3, 4, 5. How about now?
No.
They're the same. How about now? Yes. Does that difference have to happen immediately? No. That could happen 20 carbons down the row. What does that mean you have to do? Someone actually already sighed, which gives us the answer to that. You would have to count 20 atoms out until you found that difference. When that difference appears, that carbon all the way back, tracked all the way back, is a chiral carbon. You don't have to go 20 atoms. It's usually 3 or 4 at most. Okay? So you have to be able to track through that entire structure to find that difference. This is why hybridization becomes important. This is why bond patterns become important. It's why recognizing line structures becomes important. You have to be able to apply that information very quickly to key off on a difference. Okay? So, our big rule, look for an atom that has 4 distinguishable things bonded. Distinguishable can be very difficult to assign. Okay? The textbook will reference planes of symmetry. Okay? Planes of symmetry are fantastic. They do allow you to identify if a molecule is achiral very, very, very quickly, if you see the plane of symmetry. If you don't see the plane of symmetry, you spend half an hour searching for a plane of symmetry that you don't find. Okay? Which means it could be achiral, or it could be chiral. So that becomes the confusion with planes of symmetry. This is an internal plane of symmetry in this molecule. Okay? Because it's a tetrahedral carbon, I can cut through half of the bond. So if we turn this structure a little bit, let's see, which way do I want to turn it? Let's turn it green, fudge, white. Red, white. Okay, so we took this molecule and I just turned it. So there's the green, white. Okay, that's technically like that. Oh, fudge. And we turned it so that it goes into the plane. Okay, as we do that, that's going to pull this red one out front, and the white one's going to pull in back. So we're taking that and turning it. Kind of, sort of. Okay. In that drawing, do you see a clear internal mirror plane? No, only when we turn the molecule so that it is perfectly aligned to nail down the internal mirror plane do you see it. Yeah, that's kind of dumb. Okay? What are the odds we're going to show it so you can see the perfect internal mirror plane? No. Also dumb because we're literally drawing it so that you can't see the atoms as clearly. Okay? So we actually make it more difficult to interpret the drawing by aligning it to find that internal mirror plane. So be careful with internal mirror planes. Sometimes they're great. Sometimes they aren't. Okay? So, some examples. Do you see an internal mirror plane in either of these drawings? Okay? We had one adventurous yes. Where's the internal mirror plane? You said yes, didn't you?
No.
Maybe it would help to change our view on the molecule or do a rotation. Are these two structures identical? Yeah, what did I do? Just rotated. You see an internal mirror plane? Yep, there it is. Okay. Was it in the initial drawing? Yes, it actually was. What? It's the plane of the paper. The plane of the paper cutting literally the molecule directly in half all the way across is an internal mirror plane. People are like, you can see that? No, that's why it's stupid to look for internal mirror planes. Okay? But it's there. Right? How about the top one? You mean you can't just cut that straight through the plane of the paper? Wouldn't that cleave all those bonds? It would if we acknowledge that what we've got drawn here is a Lewis structure. And the problem with Lewis structure is that it doesn't show you shape. And as soon as we show a little bit of shape by drawing in that wedge, do we have that mirror plane? Nope. Okay? So if instead we'd gone through and said bromine versus CH3 versus CH2 versus, oh, there's only 3 groups, so it must be a chiral. There's an implied hydrogen, 4th group, 4 groups connected to that carbon is a chiral atom. That went by a little quick. Let's rewind that a little bit. If we tried to just find 4 distinguishable groups and we look at that carbon, 1, 2, 3, right? Where's the 4th? Okay. Do we see it? No, what were you responsible for doing at the very beginning of this unit? Acknowledging that there are implied hydrogens to satisfy octets on our carbons, which means there are indeed 4 distinguishable groups. This is the first place where implied hydrogens will come back and bite you. Yay. Okay. Kind of, sort of? Okay. By introducing this concept of chiral and being non-superimposable on the mirror image, it immediately necessitates having to bring in some new definitions. Okay? Because now I have my hands that are non-superimposable on mirror image. An individual hand is chiral. But what is the relationship between 2 hands? Mutual? Respectful? That was a relationship joke for the record. Or not record, depending on if you laughed or not. Okay, we don't have a word because they're not identical, right? They're not different. We could call them stereoisomers, but it turns out there's going to be multiple ways that we can get stereoisomers because we had geometric isomers, okay, cis and trans. The bromine structure is not going to generate cis and trans. Okay, I have nothing to be cis or trans about. So I need a new name to describe that. Okay? The new names that come out, we get 3 of them. We get enantiomers, we get diastereomers, and we get meso. Because it always comes out, don't feel bad if you can't pronounce any of these. Okay? The hardest one, for whatever reason, appears to be diastereomer, which becomes disasteromer. That's fine. Okay, I don't care. Okay? Those are our definitions. Those definitions can be difficult to manipulate, just like it was difficult to identify different versus isomers versus identical. Okay? The way we were able to identify those was jumping into a classification tree, okay? A flow chart that allows us to come up with ways to identify those. This should look really familiar because up to our same atom connectivity, all of those questions are the same. We're now just adding this question of, do we have a chiral atom? Do we have mirror images? And again, same deal, chiral atoms again. So we're really only adding 2 questions. Are there chiral atoms and are they mirror images? The order in which you follow this flowchart becomes important. We'll very often get people going through and going, oh, they're mirror images of each other, so they must be enantiomers. So let's take a look at a quick example. Are those mirror images? Yes. Are those enantiomers? No. What are they? They're identical. Okay? So don't jump all over they're just being mirror images. Okay? Just because it looks like a mirror image doesn't make it an enantiomer. We also have to answer all of those questions above. Okay? Kind of makes sense? Okay, let's throw in one more on this. Because more is always better. Okay? Wedges. Wedges immediately set us up down that category of, oh, I've got 4 different things. And in fact, if I look at that position, I'm going to have 4 different bonds on it, right? So that must mean because, well, it's not exactly, but if I flip that, then it would be a mirror image, right? So they must be enantiomers. They're still identical. A wedge does not mean you have a chiral atom. Okay? And before you start flipping out on us saying that it's all organic chemists' fault for showing wedges and now confusing students with trick questions, it's you that drew wedges inappropriately, which led you to the wrong conclusion, which then led us to say, well, crap, we now have to test on that to make sure people don't make that mistake. Sorry, that's your fault. Well, arguably it's my fault because I made the mistake before you, right? Right? So we have to watch out for that. Wedges and dashes are good things to be considered seeing and looking for. Oh, there might be a chiral atom. Take a deep breath and make sure you've got 4 distinguishable groups around that wedge. Was it necessary to show it as wedged and dashed? Okay? In this case, it was not. We could have just shown it as a bromine single bond. There was no need to add that extra information of wedges and dashes. How are we feeling? Don't worry, you still got 40 hours. Right? Ish? Identify relationships. Okay, so we got 4 structures up here. If we want to identify the relationships, how many different relationships do we need to identify? So for instance, I could relate these 2 to each other, right? So that would be 1, 2, 3, 4, 5, 6. There's 6 relationships up there. So that's effectively 6 questions. On a test, you should be looking about a minute per question to figure that out. It's a bit fast, minute and a half. So 6 questions. I'll give you 7 minutes. So what do you guys think? That was about 7 minutes.
I was thinking like Chiral.
Did you get them all? Not bad. 2?
All probably wrong.
Yeah, that's not. So one thing to address here, because we said there were 6 possible. We got a couple. I got two of them figured out, so that's 20% right. So 20%. It's not quite that bad. Okay. That would be if the entire test was this. Then yes, I would agree with that assessment. The entire test is not this. There's other questions that manipulate in there as well. Okay. So don't get too down on yourself if you're having a hard time with this. This is whatever I posted in the announcement. I think 4 or 5 questions. Okay, out of 45-ish.
Are they multiple choice?
So some are multiple choice, some are short answer. Check the announcement.
No, I mean, but are all of these?
I won't answer that.
Because it's a short answer, no.
So let's take a look. Did anybody notice anything right away when looking at this? Bottom right one. What's wrong with the bottom right one? Why do you flag that? Okay, that carbon is not the same in all the other cases. Okay? Does that mean it is different from the rest? It's one of those weird things with different, right? Different meant different formula. Okay? In this case, all we've done is change the location of a CH3 versus a, what was connected up there? A hydrogen. So all we're doing is changing the location of where I have a hydrogen versus a CH3. We're just exchanging those 2 groups, which means they have the same formula. Different connectivity, which means structural. Okay, so there we go. We solved 3 right out of the gate. That's fun. Okay. So, where do you want to go now? The bed doesn't count. Top 2? Okay, if we compare the top 2, if you take a look, the structure, overall structure aligns really quickly, kind of directly on top for the most part. So we're already mostly in that superimposable configuration. As we check that superimposability out, we'll notice wedged and wedged, right? Okay. So that superimposes. What didn't superimpose? That OH. Okay. So most of the structure superimposes except for one part, which means we're probably looking at stereoisomers, pushing into that definition a little bit further. That's where we encounter chiral atoms. Okay, and then the next fun question, mirror images. So for sure we have chiral atoms here, and I would actually argue the chiral atoms are going to make this question a little bit easier. Where are the chiral atoms? So there are our chiral atoms. If we take a look here, what happened to it? It stayed the same. If we look here, it changed. Let's key off some good words here. How did it change? For instance, if we took a mirror and sliced it through the middle of the structure, it reflected across the mirror, right? So this was a mirror. So one mirrored, the other did not. Okay, if only one thing mirrors, could the entire molecule be a mirror image? No. What does that mean? They're not enantiomers, which leaves us with diastereomers in that category. Kind of, sort of.
I don't get the whole mirror image.
The mirror image thing is a tricky one to do. If you don't get that at this stage, what I would recommend you do is just follow the flow chart. What I'm trying to do is provide a shortcut. If you don't see the shortcut, don't do it.
When I was doing the homework, it also described the stereoisomers as having two or more items, but it has to not.
So there's lots of definitions that can go with these. Diastereomers will have to have at least two chiral atoms. Okay, that is a requirement. So if you look at a structure and see only one, it can't have a diastereomer. Okay, so that could be an out. Okay, there are two here, so it could be diastereomers. Enantiomers could have 2, 3, 4. So really the diastereomer versus enantiomer line really only segregates if you have one chiral atom, then you know you're looking for enantiomers or identical. Okay? If you have more than 2, you really kind of have to look at both. What happens this direction? Everything mirrored. If everything mirrors, they would be mirror images of each other. Are they superimposable? So the superimposability, note the line is still a line so that we can overlap directly across, right? Would the OH superimpose with that? No. Does the bottom overlap? No. Which means they are enantiomers. Okay? That is a challenging one to go through and do. So superimposability is a part of that. The other one is what is the mirror image? To figure out our mirror image, what we could go through and do, and this is how I would always go through and do a test, which is fantastic. I hated it. What have I just drawn? That, I'm guaranteed, is the mirror image of the bottom structure. Does that superimpose on the top structure immediately? No. Why not? The OHs are on the wrong side. So what am I going to have to do? I'm going to have to flip the structure. Oh, because someone asked that. We're flipping it on that kind of vertical axis. I'm going to say that's the Y, right? We're rotating about that. You were welcome to laugh at my poor referencing of axes. As we flip that structure around, the double bond's now going to go to the other side of the structure, yeah? Okay. That OH was wedged coming at you. If I flip around, what happens to it? Becomes dashed going away. That bottom one was dashed going away. If I flip it around, becomes wedged. Are these superimposable? Yes, those directly superimpose. Okay? So on what I know to be the enantiomer, directly superimposes with the original, right? Which means the relationship between those is also enantiomers. See all the drawing that I had to do? That's what I would do. Okay? How much time does that take? A lot. Okay? Too much. That's fine. Too much. What's your answer when you see this question? Pick a random answer and move on. Okay? Or leave it blank, try and get the rest of the exam finished faster so that you can come back to this one and try and stumble your way through it. You've already acknowledged it's going to be a challenging question for you. You should really only be attempting it if you're confident in all your other answers. Make sense? Yes.
Do we get this flow chart?
No. It's a fair question, but no. Last relationship here. Okay. It's also a diastereomer. Okay. Just for the record, when it comes to flowcharts and extra things on exams, we've actually tested this. Grades go down. The more information we give you on like supplements like flowcharts or formulas, your grade performance goes down. Okay. You might be like, well, why is that? Well, if I tell you a bunch of stuff is there, what do you do with it? You don't study it. When you get to the exam, you don't know how to use it, and you end up screwing it up. Okay. If we say that you have to memorize it, you spend the time to learn how to use it, and then you don't have to use it again. Okay? Sorry, it's just the way the statistics have worked out. Seen it time and time again. Some cases, it's actually a negative, like a really big negative result, like 10 to 15%. We give you a bunch of information and you bomb it hard. Okay? Do you want to look at lowest energy conformers? We got like 3 minutes, just for the record. Yeah? Okay. So we looked at the 1, 2. I already did that one. So if we went through and were asked, say, for the trans 1, 2, okay, and I want the lowest energy conformer. As soon as I say the word energy, you should immediately be doing what? Newman projection is a big red flag, but this is a cyclohexane, right? I could draw a Newman projection in the cyclohexane, except we spent all that time doing what? To learn that we don't have to do Newman projections for chairs if we acknowledge that our lowest energy needs to be equatorial. Okay, so we don't have to go to Newman projections. We could immediately try and draw a chair and start dropping on our positions. That can work sometimes. Sometimes it doesn't. Okay, so let's go ahead and try that. If I want a trans 1,2 dimethyl cyclohexane, where do I want to put position 1? Okay, that looks like a good position. There's position 1. Okay. Trans 1,2. I know I want equatorial, so what should I do? Draw it equatorial. That is equatorial aimed where? Up. That's going to be an important question, but I'm actually going to erase that for the moment. It then says 1, 2. It's not specifying which way I directionally number this, so it actually doesn't matter. Okay, so I'm going to go to the easier position in front, 2. I had to put on a methyl, right? At the 2 position. I want lowest energy, so equatorial. Whoops. For those of you understanding the whoops, that has to do with how we would draw our axials and equatorials. And we've now got 1,2 dimethyl cyclohexane. Remember I did ask that question. Which way was the red group aimed? Which way is that purple aimed? Up and down, that would be trans. Cool, that actually worked out okay. Right? I have one going up, one going down. Fantastic. And I drew it in my lowest energy conformation. Okay, so let's try the next one. Cis 1,3. Let's actually do something different. We'll keep it with trans. Let's do the trans 1,3. Where's my 1? Wherever we want. Okay, there's my 1. Where do I want my methyl to be? Equatorial. If that's my 1 position, where's my equatorial? Up or down? Down. Okay. 3 position ultimately doesn't matter, so I can go over to my 3 position, right? And I want to put in my other equatorial, right? Okay, equatorial down. And there we go. We would have, and I keep drawing that in the wrong freaking position. There we go. There's my 3 position for 1, 3. So I've now got my trans 1,3 dimethyl cyclohexane, right? Some people are like, yep. Some people are like, no. What's your no?
It's not trans.
Question said trans, which means while this may be a lovely low energy conformation for a 1,3-dimethyl cyclohexane, it didn't answer the question. The question said the lowest energy for trans. So what am I going to do to that 3 position? Draw that up. Okay? So that this way they are now trans, yeah? What becomes the problem if I make that trans? That's now axial. And then axial would inherently be higher energy, which means this must be wrong. So what do we do? Okay, moving the 1 somewhere else is going to do absolutely nothing. Because this is 1, 3. And moving the 3 doesn't do anything. It's still 3. Ring flip. Okay, so the 1 was down initially. When I go through and do that ring flip, it was equatorial. When I ring flip it, it becomes axial. The 3 position was axial. When I ring flip it, it becomes equatorial. So this is still up, down. Awesome. This must be my lowest energy conformation. And we're still getting a no. What do you mean? It's the same energy as I started with. What's your lowest energy conformation? Either one. Doesn't matter. There is no lower energy than that. Right? Can you do trans 1, 3 where they're both equatorial? No. One will have to be axial, one will have to be equatorial. Make sure you answer the question that's asked, not the question you want to answer. Okay? With that, we need to be done.